Now then guys, I hope and welcome to this video where we take a look at another interesting problem from mathematics, and we take a closer look at the problem solving process in all its messiness and how you might look at how you might approach finding a solution to non-routine problems in mathematics. So for this video, I've chosen a problem from one of my favorite books, which is this one. It's Challenging Problems in Geometry by Posamentier and Salkind. I've used this, I think, in a previous video or previous couple of videos, and it's chock full of really good, interesting and challenging problems. Certainly haven't solved all of them as of yet. Some of them are really difficult, but I'm working on it. Okay, so it's a highly recommended book, by the way, if you really want to practice your problem solving skills. It's nice and cheap, and for the price that you pay, it's well worth it. Okay, so let's have a look at the problem. By the way, this is just before I get started, this is a fairly new YouTube channel. At the time of making this video, I've only got a few subscribers, so I'd be really grateful if you'd hit the like button and hit the subscribe button for this channel to show your support. Cheers, guys. Okay, so on with the show then. So we're looking at problem number 9 from chapter 7. Okay, and the title of this chapter is Ptolemy and the Cyclic Quadrilateral. Ptolemy and the Cyclic Quadrilateral. That's going to be important, by the way, because it gives a big clue as to what we're going to need to be doing to solve this problem. So the problem is as follows. If square ABCD is inscribed in a circle, so I need to make sure that I get this right, because I've got my notes here as well that I may need to refer to, but I need this to be consistent with my notes. So I've put A, B, C, D. And a point P is on the arc BC, so P might be here. It could be anywhere on the arc BC. Let's suppose it's there. And prove that PA plus PC over PB plus PD is equal to PD over PA. Okay, so what we're talking about here are the lengths, so the distances. The distance PA plus the distance PC over and so on and so forth. Okay, so my first attempt at this, which I made without really looking at the title of the chapter that I was working from here. So I tried to, my initial attempt therefore was a bit wrong. Okay, I'm gonna explain why. Part of the problem solving process is that sometimes you come up with ideas that turn out to be wrong, but there might still be something in those ideas that you can take away. So I'm going to describe the initial idea that I had and why I started to feel that it wasn't going in the right sort of direction. So initially what I did then was to join up all of them, because we're interested in these distances, PA, PC, PB, and so on. So it seems natural for me to connect all of these points up. Okay, and I also drew in the diagonals of this square. Okay, so because ABCD is a square, that means that these red lines here that I've drawn, if you can see them by the way, BD and AC, they are going to be diameters of this circle. Okay, because the angles ABC and the angles ADC are both right angles, therefore AC and BD are going to be diameters. Okay, so my initial idea here was to recognize that also angle, because again AC is a diameter, APC, angle APC is going to be a right angle. Okay, so it's a right angle. And I also recognize that based on similar reasoning, angle BPD is also going to be a right angle. Okay, I thought I was making some progress here until the next step that I decided to take here was to start thinking about the areas of the triangles APC and BPD. And at this point, this is where things start. I started to get the impression that I wasn't really going in the right direction, for the simple reason that I was using the formula for finding the area of a triangle. Now, you might think, well, what's the big deal about that? When I try to solve problems in pure geometry, I always try to solve them, if possible, using techniques that I've seen in, for example, Euclid's Elements or Apollonius's conics. And in Euclid's Elements, Euclid never introduces a formula, for example, for finding the area of a triangle. Okay, it talks about areas of triangles, compares the area of one triangle with the area of another triangle, or with the area of some other polygon, for example. But the area of a triangle tends to be spoken about really in comparison with other areas, not as an absolute thing. So he never says anywhere in the Elements, the area of this triangle is such and such, and uses the typical formula half base times height for the area of a triangle. He does establish the fact that the area of a triangle is half the area of a certain parallelogram, for example, but never actually uses the formula for the area of a triangle. So I thought that introducing the formula for the area of a triangle in this context just seemed a bit wrong. Okay, in other contexts, I wouldn't necessarily feel the same way, but I got a bit of an icky feeling when I introduced it. But the idea was that triangle APC, with it being a right angled triangle, it's just going to be half times, where is it, APC? It's going to be half times AP times PC. And triangle BPD, because that's a right angled triangle, is going to be a half times BP times PD, I guess. Yeah. And okay, it was at this point that I read the title of the chapter, Ptolemy, excuse me, and the cyclic quadrilateral. That kind of gave the game away for me. But the important thing is, when it comes to problem solving, is that you're prepared to try out your ideas, to just follow through on the ideas that you have. Sometimes you might have the impression before you've actually tried out an idea that it's probably not going to work, or it's not going to take you in the direction that you want to go in. It's still worth trying it out, unless you've got something better, another idea to go with in the meantime. If it's your only idea, just go with it, because you never know, it might actually stimulate something along. It didn't in this case, it was something else, but in some of the other videos that I've done on problem solving, I've explained how actually doing something which I didn't necessarily feel was going to work, and actually in and of itself turned out not to quite be the right direction that I needed to go in. It kind of motivated me to do something else based on what I saw in front of me, and which did take me in the right direction. Okay, so just be prepared when it comes to solving problems to sometimes try something and it doesn't work. But sometimes you might try something that you think is not going to work and kind of doesn't work, but it stimulates some other idea. Okay, so I didn't like this. I didn't really like the direction that it was going in. It might be possible, by the way, to use this kind of idea to solve this problem. It's just I didn't pursue it any further. Okay, so then I saw Ptolemy's theorem. Okay, the chapter title, Ptolemy and the cyclic quadrilateral. If I'm honest with you, yes, I had to go and look up Ptolemy's theorem. I couldn't remember it off the top of my head. It is something that I've come across before, but Ptolemy's theorem effectively says that given a cyclic quadrilateral, it doesn't have to be a square, although a square is a cyclic quadrilateral. Just any old cyclic quadrilateral. So I'm going to use ABCD again, but this is a different situation. If we use ABCD, and if I draw in the diagonals of this cyclic quadrilateral, then what we get is that the product of the diagonals AC times BD is equal to the sum of the products of opposite sides. So AB times DC plus BC times AD. Okay, that's Ptolemy's theorem. So that distance AC times that distance BD is equal to the product of those two distances plus the product of those two distances, BC and AD. Okay, so that's what we're going to be using. Now, the next thing that we've got to do really is to identify suitable cyclic quadrilaterals in here, because there's cyclic quadrilaterals all over the place in here. Okay, and this is why I'm going to have to refer to my notes, because you've got to get the right ones. It just takes a little bit to identify which cyclic quadrilaterals you want to focus on. So I'll rub this off for now. It's also worth bearing in mind that because ABCD is a square, that AB is equal to BC is equal to CD is equal to AD, and also the length of AC is equal to the length BD. Okay, so these are the sides, and these are the two diagonals. So the cyclic quadrilaterals that we're going to be looking at are quadrilateral ABPD. ABPD. So this the quadrilateral with vertices A, B, P, and D. And we're also going to be looking at cyclic quadrilateral, and I want to check my notes to make sure I've got it right, APCD. APCD. Okay, so we're going to take these one at a time. It's a fairly straightforward calculation, by the way. So in ABPD, the diagonals are going to be AP times BD. And this is going to be equal to the product of BP times AD plus AB times PD. And in APCD, the diagonals are PD and APCD, AC. And the opposite sides are PC times AD plus APCD, AP and DC. Okay, so then we consider the ratio. Which way around do I want to? Right, so I want to do this. Right, so PC times AD plus AP times DC over BP times AD plus AB times PD is going to be equal to PD times AC. PD, not PA. PD times AC over AP times BD. Okay, and then we're going to need to use some of this information up here. So we know that, for example, AD AB are all equal, AP and DC, sorry, of course. And then over here, we've got that AC and BD are equal. So effectively, I can change all of these to just, let's say, AB plus AP times AB over BP times AB, plus PD times AB equals PD times AC over AP times AC. And then it's kind of a cancelling down sort of thing. Now this could be formulated in a much more Euclidean-ish sort of sense. But we're going to use kind of more modern techniques for this, just to save a bit of space. So I can effectively take out, these are, we think of these as just numbers, right? So I can take AB out, which is not necessarily how Euclid would have viewed this, as these would just be numbers. These would be lengths, and PC times AB would be kind of a rectangle with sides of length, PC and AB and things like that. But we'll think of them as just numbers, just to, again, save a bit of time and a bit of space. So we can take the AB out as a common factor here and cancel out. So we're just going to be left with PC plus AP over BP plus PD equals PD over AP. Okay, so we've got it doesn't matter whether I write AP or PA, it's both, the distance from P to A is the same as the distance from A to P. So we've got AP PC over PD plus PD equals PD over PA. And that's the demonstration of this particular theorem, or the solution to this particular problem. So it all hinges on Ptolemy's theorem. I'm not going to present a proof of Ptolemy's theorem in this video, but by the way, it is one of the questions, or one of the problems set in this book. It's from the same chapter, chapter 7, problem number 1. But I did try to find a solution to it myself, to prove Ptolemy's theorem myself. I've got to be honest with you, I didn't manage to do it. There's a little trick involved with it. Once you know what the trick is, it's not difficult at all. In principle, it's just arriving at a point where you figure that trick out. How that trick was figured out in the first place, I have no idea. That's an entirely different thing, but we'll leave the solution to this problem there, and that brings us to the end of this video. Thanks for watching, guys. Cheers.